right, you guys. Sorry, third hour. It's the only day I have to be gone for Blake's picnic. So you just did a bunch of graphing, and now you're going to do growth and decay notes, okay? So we're just going to do like the basic exponential function. So this equation is something you're going to need to know. So it's y equals a times b to the x power. Okay, I'm going to write it down here just so we can see it a little better, and we can label these parts. A right here is the initial amount. This is how much you start with, or how much you start with anything. Not always money, but just how much you're starting with. Okay, B is how much it's changing by. Now, B might be a growth or a decay, and we'll talk about that. Now, this X is going to be like X divided by some number, and this is how often, like every 12 months, every 10 days, and they're going to be different units. So the units are going to change in this depending on your story problem, but it's how often something is happening. So we have growth. Obviously, you want, like, growth means things are going to increase. In order for it to be considered an exponential growth, your B value has to be greater than 1. Okay, your B value has to be greater than 1. So A is the initial, and B is the growth factor. Sorry, I'll move my hand. Now, in order for it to be a decay, you think, oh, then it's going to have to be negative. No, in order for it to be a decay, B is going to be between 0 and 1. Okay, B is going to be between 0 and 1. It's going to be a decimal. Okay, because when you multiply by a decimal, it gets smaller. And a decay means it goes down. So when you multiply by a decimal, it's going to get smaller. So same thing here. A is the initial, and B is the decay factor. Kind of small, sorry guys. So that's what you need to know. Y equals A times B to the x power. This is an exponential function. So let's do some examples. Bacteria growth. An experiment begins with approximately 400 bacteria. So look at this. This is my initial value, which grows at such a rate that their population triples every hour. So those are like huge words right now that I know I'm going to have to use. Write a rule that represents a situation. Explain what each piece of your rule stands for. So I know it has to be y equals a times b to the x power. Okay, so I know a is my starting value. So y equals 400 because that's my initial amount. I can put initial here. Okay, this is how much it's changing by. Well, it says that it's triples. So this is going to be 3 because I know that means it triples. It's changing by that amount each time. And this x is divided by how often it happens. Well, it looks like it's every hour. So x divided by 1, but this is in hours. Okay, it's really important that we label our units. So here is our equation. Y equals 400 times 3 to the x divided by 1. Okay, so the next one is find the number of bacteria 3 hours after the experiment begins. So let's write our equation. Y equals 400. It still triples. 3 hours. Well, it's every 1 hour. So x is going to be every 3 divided by 1, because every 3 hours equals. So let's do that in our calculator. So I know it's going to be 400 times 3 to the third power. Now, order of operations, or you can just type it. I think you can type in your calculator. I have a graphing calculator, but if we do order of operations, it would be 3 to the third power times 400. Okay, and I have 10,800. Or you could put it in like this in your calculator. It'd be 400, and then parentheses, 3, parentheses, to the third power. Okay, equals 10,800 bacteria. That's how much bacteria would happen if it triples every 3 hours. Okay, find the number of bacteria an hour and a half after the experiment begins. So again, I'm starting with my initial value is 400. It triples every 3 hours, and the time now is 1.5. So 1.5 divided by 1. Okay, again, this is this x, this unknown. We're just filling in the hours they give us. So I can type that in. 400 times 3 to the power of 1.5, 2,078 approximately. 2,078 bacteria. And I just rounded to the nearest whole number. Find the number of bacteria 4 hours before. Oh my gosh, how are we going to represent 4 hours before? How do you think we would do this? 4 hours before would mean it's going to be a negative because it means it happened before. So y equals 400 times 3 to the negative 4 divided by 1, which we know is just negative 4. So 400 times 3 to the negative 4th power. So I'm going to type in my calculator. 400 times the quantity of 3 to the power of negative 4. 4.938. So I'm going to say it started with approximately 5 bacteria. And you know it should be smaller than 400 because that's what we initially start with it. But it's starting to say that it's 4 hours prior to that. So that's why your answer should be smaller. All right, here's a new one. Suppose 2 mice live in a barn. The number of mice quadruples every 3 months. Okay, so let's use our equation back up here. Y equals the initial value times how much it changes by times by the time. So y equals, I started with 2 mice. Quadruples goes with 4. Okay, and then I don't know how many months, but it changes every 3 months. So that's going to be x divided by 3. And let's label this. This is going to be my months. This is what I start with. I'm going to put the initial, and that's my growth factor. Okay. So now it says how many mice will be in the barn after 2 years. This is where you need to be really careful because this is years and this is months. So we can't just plug in 2 for x because 2 years does not convert to months. So let's convert 2 years to months. So that's going to be 24 months. So now I can just plug it in. Y equals 2 times the quantity of 4, and then 24 goes in for x. So 24 divided by 3, which I know is 8. So y equals 2 times the quantity of 4 to the 8th power. So type it in your calculator. 2 parentheses 4 to the 8th power. Ooh, pretty big number. 131,072 mice. And again, it's round to the nearest whole number because we're talking about a rodent here. It's disgusting, but yes. All right, so make sure you're getting that in your calculator. If not, just stop for a minute and go back and watch this so you can get in your calculator. So this is all growth. All right, now we're going to go into some like decay, half-life. Like when we talk about like a lot of things in science, like their half-life, how long they're going to live, we represent it with called half-life. And we're talking about half-life, it's always going to be like 0.5 is how much something changes. So when you hear the word half-life, your decay factor is always going to be 0.5. So it says assume carbon-14 has a half-life of 5,730 years. So I know I'm going to have to use that. Write a rule to represent the situation if a scientist starts out with 24 grams. Explain what each piece of your rule stands for. All right, so I know y equals, I started with 24. That's my initial. Okay, it's half-life, so it's changing by 0.5. And I know that that x divided by 5,730, because that's how much, it says half-life of 5,730 years. Okay, and we're talking about years here, so make sure we're just labeling this so our units are going to match. So that's what I start with. This is my decay factor. So I know it's going to go down this time. It's going to get smaller. It says how much will she have in 11,460 years? Round to 4 decimal places. So y equals 24 times 0.5. Now, 11,460 divided by 5,730. I would do that first on your calculator just to see what you get. Okay, and that's 2, whole number of 2. So really this is 24 times 0.5 to the 2nd power. That's a lot easier to put in my calculator. 24 times the quantity of 0.5 to the power 2, and I got 6 grams. Okay. How much will she have in 1,910 years? All right, so again, y equals, started with 24. It's half-life, so my decay factor is 0.5. And I have 1,910 divided by 5,730. And again, I'm going to do that on my calculator. 1,910 divided by 5,730, 0.33. So this is going to be 24.5 to the 0.333 power. Now I can type that in my calculator. 24 parentheses 5 parentheses to the power of 0.333. So it looks like I have, oh, did I not divide that right? Oh, I put 5, not 0.5, sorry, 24 to the power. The reason I knew this is it got bigger. I know it's a decay factor, 0.5 to the power of 0.333. There we go. 19.0. Oh, I only have this rounded to 3, so this is okay, 0.53 grams. If your calculator gives you something else, it round to the nearest 4. This one's programmed for 3 for some reason. I don't know why. It's totally fine. All right, how much carbon was there 2,865 years before the scientists started to use it? So remember, before is going to be a negative. So I have 24, or y equals 24.5, and then negative 2,865 divided by 5,730. So I'm going to do that first. Negative 2,865 divided by 5,730, negative 0.5. So 24.5 to the negative 0.5. All right, so 24 times 0.5 to the power of negative 0.5, 33.941. 33.941 and grams. And you guys, you know what? This is a decay, so it should be bigger than 24 this time because it's going down. Where our last one should have been smaller because it's going up. All right, last couple. A half-life of iodine is 4 days. If you start with 40 MCI samples of iodine 124, how much will be left after 37 days? Okay, so it's half-life, so I know right away it's going to be 0.5. Iodine 124, this is just the compound we're talking about. 4 days, it starts with 40. So again, identify all these numbers. Starts with, I know has to be my A. Okay, it's half-life, so I know my decay has to be 0.5. And it says it's every 4 days, so x divided by 4, and I know this is days. Okay, if I said every day, it'd be x divided by 1. All right, so 40, so now I'm going to plug in 37. So 40 times 0.5 to the 37 divided by 4. 37 divided by 4, 9.25. So 40 times 0.5 to the 9.25 power, and again on my calculator, 40 times 0.5 to the 9.25. I'm going to get 0.066. And again, if you have like 0.0657, your calculator is rounding more than me, and that's totally, totally fine. This calculator, I just realized, is programmed to round to the 3 decimal places, and I told you on here 4, so no big deal. And this is milligrams? Oh yeah, I can change this to milligrams. Okay, and again, like if I rounded correctly to 4, it'd be like 0.0657. All right, a wizard has told you that he'll give you $1 today. It will triple every day for the next year. Which equation represents the wizard's gift? So you start with $1. It triples every year. X divided by 1 is the same thing. Well, that doesn't look like that. There's no exponent. This is a plus. So this is my only option. And why does it look different? Well, it starts with 1. And necessarily you don't have to put 1 there. So that's why it looks kind of different there. Okay? All right, you guys are going to work on your growth and decay homework now. Have a great day.